Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Latent Space. Joining us is Jeff Dean, Chief Scientist at Google DeepMind. His central claim: the future trajectory of artificial intelligence is determined not by algorithmic innovation, but by the energy cost of moving data across silicon. This physical constraint reshapes everything from model architecture to the economic purpose of frontier systems. Here is his technical reasoning. Jeff Dean, Chief Scientist at Google DeepMind, opens with a claim that inverts conventional computing assumptions. Batching is not a throughput optimization technique, but an energy survival strategy dictated by chip physics. The standard view treats batching as a method to serve more users simultaneously or increase system utilization. Dean reframes this entirely through the lens of energy economics. He points to a brutal physical asymmetry. Executing a single mathematical operation, such as a multiply, consumes approximately 1 picojoule of energy. Moving the data required for that operation from SRAM memory to the compute unit, however, consumes roughly 1,000 picojoules. This creates a 1,000 to 1 energy penalty. Processing a batch of 1 means paying this massive data movement tax for minimal computational work. Batching amortizes that cost across hundreds of operations, transforming what appears to be a software scheduling decision into a fundamental energy arbitrage. Efficiency in his framework is not about optimizing code, but minimizing the physical distance and frequency of data movement. This energy-centric worldview produces a second inversion regarding the economic purpose of massive frontier models. Industry consensus treats trillion-parameter models as premium consumer products, the pro or ultra tiers that command higher pricing. Dean presents an alternative function. These behemoths exist primarily as manufacturing molds for smaller, cheaper descendants. He outlines a distillation cycle where the massive frontier model transfers its knowledge into a flash model, a compact, fast, inexpensive variant. The performance trajectory here disrupts standard product hierarchies. The flash model of the current generation consistently matches or exceeds the pro model of the prior generation. This implies that the giant model is not the end product, but the production apparatus. The best AI is not the large brain in the cloud, but the hyper-efficient distilled version that runs ubiquitously across Gmail, YouTube, and other services. The giant exists to teach the small how to think. Dean's latency analysis produces another counterintuitive conclusion. Conventional reasoning assumes that since humans read at a few hundred words per minute, generating text faster than human reading speed yields diminishing returns. Dean argues that extreme generation speed is not for human consumption, but for internal model reasoning. He envisions systems generating 9,000 tokens of hidden chain of thought, exploring hypotheses, error checking, debating alternatives before discarding them, and presenting the user with 1,000 tokens of refined output. Latency in this model is not delivery speed, but the budget for hidden intelligence. Slow models cannot afford deep reasoning before responding. Models generating 10,000 tokens per second can perform extensive internal deliberation without the user experiencing any delay. This reasoning framework leads to an ontological shift regarding the nature of symbolic versus neural computation. For decades, computer science maintained a clear division. Neural networks excel at fuzzy tasks like language and vision, while precise tasks like geometry or formal mathematics require symbolic systems discrete, rule-based logic engines. Google itself deployed specialized systems like alpha geometry. Dean declares this era finished. He reveals that Google has abandoned the specialized symbolic approach in favor of a unified neural model. His justification forces a rethinking of human cognition. Humans do not possess a discrete symbolic logic module in their brains. Mathematical proofs are not stored as formal symbols, but as distributed neural representations that emulate symbolic reasoning. AI, he argues, should follow the same architecture. The new Gemini models absorb geometry and mathematics not by adding a symbolic calculator, but by training the neural network to internalize these logical structures directly. The general model has consumed the specialist. Dean's final inversion concerns context windows and memory architecture. Current discourse assumes that as context windows expand to 1 or 2 million tokens, we approach a natural limit. The model can process a book, but not an entire library or a lifetime of personal data. Dean dismantles this constraint by introducing what he calls the illusion of infinite attention. He describes systems under development at Google that create the user experience of the model, attending to trillions of tokens simultaneously. Every email ever written, every photo ever taken, every document ever created, The architecture borrows from search engine design rather than traditional language models. The system does not hold trillions of tokens in active memory, which would be quadratically expensive. Instead, it employs hierarchical retrieval. A lightweight filter selects the top 30,000 relevant documents. A smarter filter narrows that to 117, and the heavy-duty frontier model reads those 117 inches depth. This renders the context window effectively infinite. A personalized model capable of retrieving from an individual's complete digital history will, he argues, fundamentally outperform any generic model, regardless of the generic model's intelligence. Dean's framework reveals a unified engineering philosophy. Intelligence is not an abstract algorithmic problem, but a system constrained by physics and energy. Whether amortizing picojoules of data movement, distilling massive intelligence into efficient packages, or replacing symbolic logic with distributed neural patterns, efficiency is the mechanism that unlocks capability. The question becomes, when intelligence becomes as inexpensive and rapid as moving a byte of data, what happens to the economic value of human reasoning? If you're interested in the video featured in this episode, click the link below to watch the original.